Thank you, David, and I appreciate the invitations from the organizers to speak. It always is delightful to come back to Notre Dame. So today, well, I'm Martha Precup. David said it, I'll say it again. I forgot to put my own name here, but today I'm talking about dimension stability for Hessenberg varieties. And some of the theorems in this talk and a lot of the work in this talk is informed by collaborations, both with Rebecca Goldin and Megumi Harada and Colleen Robichaux, who spoke earlier yesterday, in fact. So I am going to spend some time on the definitions and some examples, and then we'll sort of hop into some of these results. So the lovely thing about speaking the second day and not the first day is many of the definitions have already been placed on the board for me, but I will get started. This talk is going to focus on the general linear group. Some of what I say generalizes for arbitrary complex reductive groups. And just like Melissa did this morning, I'm going to take B. I'll borrow the notation of just B is going to be upper triangular matrices. And Hessenberg varieties are subvarieties of the flag variety. So I like to denote the flag variety by script B sometimes, okay? Or also as cosets G mod B. And I actually like both the sort of flag model and the coset model. So the definition of Hessenberg variety I'm going to give you is going to be for both. I'll give you one and then the other. So here, whenever I think about this thing, I'm thinking about sets of flags of complete flags, 0, B1, Bn. And then I'll identify a flag with a coset by simply taking a basis that determines this flag and putting those basis elements as the columns of a representative matrix. I like to make my basis elements columns instead of rows. It's just my convention. Okay, you always have to be a little careful. So let's start by defining Hessenberg varieties. So there's two pieces of input. So given a matrix X in the Lie algebra of n by n matrices, and given the information of what's called a Hessenberg function, so I denote a Hessenberg function by lowercase h. It is a function from the numbers 1 through n to 1 through n. And so when I say Hessenberg function, I mean here specifically for this talk that my hi is greater than or equal to I for every I. And I'm going to require that my h be weakly increasing. So given these two pieces of information, I get a well-defined subvariety of the flag variety. So the associated Hessenberg variety is the following. So I just like to write Hess. Okay, you'll see different notations in different papers. X, H. So let me start with the flag definition. I will take all flags in my flag variety with the property that when I act on the ith subspace in my full flag, I get mapped into the H of ith subspace for all I. So there's the sort of flag definition way to define this Hessenberg variety. Alternatively, if you like to think about cosets, which I do, and you like your flags to be represented by matrices, you can also describe this as the cosets with the property such that this matrix representative for your flag, its inverse conjugates X into a particular form. So such that G inverse XG is in the Hessenberg subspace associated to the Hessenberg function H. So let me take a second and write down what this means. So this would be all of my n by n matrices, where I'm going to require that the ij entry equals 0 precisely when I is greater than h of j. All right. So maybe off the top of your head, it's a little hard to visualize what that looks like. So I have some examples in just a second here. Any questions yet? Subvariety of the flag variety, but defined using two things. Here's the pop quiz. What are the two things? Hessenberg function and matrix. Okay. Any two matrices you have me. Well, it turns out if the matrices are conjugate, the corresponding Hessenberg varieties are isomorphic. So really input information is a conjugacy class. Because with that isomorphism, I can choose a particular X within its conjugacy class with the same variety. What about this Hessenberg function? Okay, so let me show you some examples. See, is there a clicker? Or no? A human clicker, I guess. That's okay. I'll just tell. There's not that many example slides. So let me just, so here's for n equals 3, I wrote down some examples of Hessenberg functions.
There is.
Oh, there's a clicker. Great. I should have gotten this before. It's giving away the surprises.
Nobody knows.
No one knows. Okay, so here we are for n equals 3. I have some examples of Hessenberg functions and Hessenberg spaces. Okay, so in this grid, you should visualize this as meaning I'm looking at 3 by 3 matrices. Here my Hessenberg function is 3, 3, 3. Okay, n equals 3. It's weakly increasing, yes. Hi greater than I, greater than or equal to I, yes. And then if you actually like sit and stare at this definition of the associated Hessenberg space, what is it? Well, if H is 3, 3, 3, the Hessenberg space is just GL3. There's like, okay, be kind of boring. But then what happens is I tweak the Hessenberg function. I can say, oh, well, okay, I don't have to make that first entry of 3. So this tuple is telling me what is H of 1. Here I'm going to make H of 1, 2. I get a different Hessenberg function. Okay. So now my Hessenberg space is all 3 by 3 matrices where I'm going to say, okay, any entry I want in the blue spots. Okay. But then the stuff below here has to be 0. Okay. So I put little zeros to indicate in the Hessenberg subspace where you would force your zeros. Yes. So this is a conference in algebraic combinatorics. And so we notice there are 5 different Hessenberg functions for n equals 3. And so my quiz question, how many Hessenberg functions are there for n equals 4? 14. Okay, there better be 14. Okay. And then you can also recognize that there's many, many ways of thinking about the data of this Hessenberg function. One way to think about it is the Hessenberg function is actually like determining a lattice path that stays below this diagonal of the matrices. Okay, so I've drawn my paths the wrong way. But maybe if you're French, you're happy because the partition of zeros is in the French notation. Okay. So, all right, then we're n equals 4, yes. I have 14 choices. I can start with sort of the maximal thing and take h of I equals 4 for all I. That Hessenberg space is just all of GL4. And actually notice like there's sort of a unique thing I can do on the bottom. And that's the Hi equals I case, right? Because I'm requiring it's always greater than or equal to I, but I could set it equal to I and see what I get. So with these pictures in our mind, I just write down a few examples. So maybe example 0 should be the sort of boring choice at the top, right? Hi equals n for all I. So then my Hessenberg space is all of GLN. And then this condition is no condition at all because I'm simply requiring that if I conjugate my matrix, I get a matrix. And similarly, I'm just requiring that the ith subspace is just another subspace of the vector space. Okay, so in this situation, my Hessenberg variety is just the full flag variety, okay, for all x. Okay, so example, what about the sort of opposite inclusion? So you can think about the sort of partial ordered Hessenberg functions. The thing at the bottom is hi equals I for all I. And in this situation, well, what is the Hessenberg variety? If I think about the flag definition, hi equals I means I'm requiring that the ith subspace be mapped into the ith subspace. And this is a variety that has been studied in the literature. It's called a Springer fiber. Okay. So I have special notation for Springer fibers. I like to write the script B sub x. Okay. It's a habit handed down to me by collaborators. Okay. There's different ways of denoting Springer fibers, so I just think about this as these are the flags that are sort of invariant under X.
Invariant shouldn't be superscript.
Yeah, I tried to do that, then it was vetoed. I have seen it as a superscript, and yeah, I agree that I like the superscript thing too. Okay. But why are they called Springer fibers? Let me just briefly write. So one thing that you can think about is you can think about this mixed space, G cross upper Borel of script B. Script B here is the Lie algebra of my Borel subgroup B. So it's just this upper triangular matrices in GLN. Also happens to be the Hessenberg space for the Hessenberg function hi equals I for all I. And this map is given by taking a pair of things in this mixed space and using the adjoint action. Mapping this down. Okay, so usually this is called mu. So I just want to write out the part when we see a map like this, when we think about, well, what is the inverse image of a fixed matrix here? We can see that we can identify it with the Springer fiber, which is why this is called a fiber, Springer fiber. And why might you have seen Springer fibers, even if you have not seen Hessenberg varieties? So a sort of famous situation that arises is that when X is nilpotent, there is in fact an action of the symmetric group on the cohomology of the Springer fiber, given by what's called the Springer representation. So Springer fibers are sort of foundational objects in geometric representation theory. They're giving us a sort of geometric realization of a representation of the symmetric group. And then in particular, the top dimensional component of this is an irreducible representation of the symmetric group. And a lot of this story generalizes in a beautiful way to other flag varieties for other complex reductive groups. So Hessenberg varieties include this really exciting, beautiful, special case. So let me just say another quick example. hi equals I plus 1. Here's another choice for your Hessenberg function. Of course, except for h of n, which has to be n. So this guy is, unlike the two sort of n cases, this guy falls sort of firmly in the middle here. Okay. So I'm thinking about flags where my operator maps the ith subspace just into the next subspace. And this has many special names. But it turns out that if you take X to be a regular semi-simple matrix, then your Hessenberg variety is a permutohedral variety. So a toric variety. The case where X is regular nilpotent also gets a special name. This is called the Peterson variety. Because it was studied by Dale Peterson, and there's some results about his cohomology due to Peterson that's in a paper of cost. One thing to take away from this discussion is the following. Okay, except for case 0. Case 0, I didn't care what the matrix X or what the conjugacy class was. These varieties are actually very different. Okay, so I have one Hessenberg function, but when I take the Hessenberg variety over and define it using a regular semi-simple matrix. By the way, what's a regular semi-simple matrix? You're conjugate to a diagonal matrix with distinct eigenvalues. So it's a very, very simple kind of linear transformation. Every standard basis vector is just getting scaled by a different value. Okay. Then I get this permutohedral variety. It's a smooth variety, toric variety. If I take X to be regular nilpotent, so my Jordan form has one big block, then I get this Peterson variety, still irreducible, but has a very different cohomology ring than regular semi-simple. This thing can be is singular, right? So these two varieties geometrically are very different. Okay. So the Hessenberg variety really depends on the conjugacy class and the non-trivial. So let me give you just a little more motivation for why you might be interested in studying these varieties if you're here at this conference, or maybe some motivation as to, why I might have been obsessing about them all these years. I was recently talking with a collaborator who was talking about their obsessive problem. Okay, so here's some variation of my obsessive problem. So when X is regular semi-simple, and here I'm going back to the scenario where H is any Hessenberg function you want. So pick your favorite. Take path, you get your Hessenberg function. You can consider the corresponding regular semi-simple Hessenberg variety. Then we get yet another action of the symmetric group on cohomology of the variety. So then the symmetric group is acting on the cohomology of your regular semi-simple Hessenberg variety. This is a different action that comes up in the Springer representation. This is the dot action. The dot action. But you can also call this the monodromy action. So if you're thinking about the dot action, you might ask, why is it called the dot action? Well, because the action was sort of defined by Tomasco in a paper where she had two different actions she was thinking about. She denoted one with a star and one with a dot. So there's the star action and there's the dot action. Okay, so if you read her sort of defining paper, she actually thinks about the equivariant cohomology of these varieties. She studies their GKM graphs, and using symmetries in the GKM graphs, she defines what she calls the dot action. And this action on equivariant cohomology then descends to ordinary cohomology when you quotient. And then this is also realized as a monodromy action by Brosnan and Schaff. Okay, so whose talk was it yesterday that talked about Frobenius character? George set me up beautifully. Okay, it's good to go on day 2. When you see a representation of the symmetric group in the wild, what do you want to do? You want to turn it into a symmetric function. It's going to be Shor positive. So people sort of knew about the dot action. It was sort of mysterious how to compute it. And then some folks in algebraic combinatorics were studying chromatic symmetric functions and realized that when they computed examples, it aligned with this dot action representation. So let me write the formal statement on the board. So if you apply the sort of Frobenius map to this representation, okay, I'm just decorating with a Q here because this is a graded thing, so I'm going to keep track of the grading. And so that I don't write something false, I'm going to put a little omega, which is just the twist that takes a Shor function and transposes the partition shape. Okay. You can ask, what symmetric function is this? And the takeaway is that this is a chromatic quasi-symmetric. So let me put some names here. So this equality was conjectured by Schresching and Wax, who also defined what a chromatic quasi-symmetric function is. The chromatic symmetric function was defined by Richard Stanley. The quasi-symmetric version was studied by John Schresching and Michel Wax, who then conjectured these two things are equal. Okay. The quality was actually proven by Brosnan and Chow, in part by realizing this dot action as a monodromy representation. So why might you be interested in this problem? Well, okay. One thing is we like to study symmetric functions. We like to study their combinatorics. And if you see a symmetric function, what's your favorite thing to do? First, write it in the Shor basis. Okay. But then once you have it in the Shor basis, what would you like to do with that? Well, you try other bases, and then you say, okay, what's the meaning of these other expansions? Okay, so if I go ahead and write this thing, I can go ahead and write it. There's some coefficient depends on H. I can write this in the Shor basis, okay, and it has to be Shor positive because it's coming from a symmetric group representation in the wild. When you run into these things in the wild, you take their Frobenius character, but then we also want to compute its G. Its expansion in the elementary symmetric function basis. And the conjecture, which has generated a lot of work, so this was first conjectured by Stanley and Hessenberg in the special case where Q is equal to 1. So the sort of ungraded version. And the graded version was conjectured by Schresching and Wax in their paper. So the conjecture is that this G expansion is in fact positive polynomials, and I should immediately say that when Q is equal to 1, this is a theorem of Hickey.
Yeah. Sorry, I lost attention for a moment. So what is S of SH? Is it
regular semi-simple Hessenberg variety?
So
this guy. Oh, thank you. Okay. Might fix. Or I should change that to an X.
Also, there.
Ah, thank you. I have a habit of saying a semi-simple matrix is S, a nilpotent matrix is N, general matrices are X, and this is the root of many problems. All right, so this is a theorem of Hikita, and now in the case when color coordinate. When Q is equal to. So it's still open in the general sort of graded case, to my knowledge. Check the archive every day, I don't know. Okay. All right, so you might say, okay, great. This is sort of a black box because they didn't tell you what a chromatic quasi-symmetric function is. I'm happy to talk more about that later, but all right, why might I care so much about Hessenberg varieties? A special case about regular semi-simple Hessenberg varieties is intriguing, but what about these sort of other Hessenberg varieties over other conjugacy classes? Why might I be interested in studying those? So I want to go back to this mu map here, where I have this mixed space G cross upper B of math frac lowercase b, which was just upper triangular matrices. And I just want to point out this sort of monodromy representation approach to things essentially takes that map and writes down the version of that map for an arbitrary Hessenberg function. Okay. So the sort of the heuristic, driving heuristic here is that now, instead of thinking about mu, which is sort of originally defined and studied as part of the study of stringer fibers, I can think about what I'll call this like mu sub h. And the sort of variation on the theme is I've replaced my upper triangular matrices with a different B stable submodule, which are exactly the matrices that have non-zero entries above my deep path and zeros below the deep path. And the fact that the dot action is given by monodromy precisely means, in fact, that all the fibers of this map see information about the representation. So let me sort of say, this is sort of the driving statement, the Benny numbers of Hessenberg varieties in fact encode combinatorics of symmetric functions, of chromatic quasi-symmetric. Of course, in the case that we're talking about, the chromatic quasi-symmetric functions are vexsymmetric. So this is maybe the sort of statement to take away from this, right? And why am I so interested in these varieties? Why am I so interested in studying their geometry? Well, there's some interplay going on here between the combinatorics of the symmetric functions and the sort of geometric data of these Hessenberg varieties. So let me give you a precise statement which sort of realizes this heuristic. Okay. So this is a theorem statement. I'm sorry, this is a very wide room. So I can really talk one half of the audience. You feel the pain of my calculus 3 students. See, where did my erase? You write down a precise statement. So here's a theorem. That's actually an unpublished work of Tomasco and McPherson. But you can also find approved version of the statement and work of myself and Eric Summers. So this is unpublished. So let's go ahead and let's take the Poincare polynomial of a Hessenberg variety. So I'm going to use n sub lambda. I told you n means nilpotent. What should n sub lambda mean? Nilpotent of Jordan type lambda. I write down my Jordan blocks. Lambda, this partition, is telling me the sizes of my Jordan blocks. Okay. Good. More people are nodding besides my graduate students, so that is a good sign. And I try not to look for them for validation. They have to hear me talk too much. Okay. So how could you compute this Poincare polynomial? Well, one thing you could do is you could try and study an affine paving of this Hessenberg variety and just explicitly compute it. And I'm about to write a theorem that says how to do that. But on the other hand, how is this Poincare polynomial encoding the combinatorics of the symmetric functions? Well, okay, look over there. The Schur expansion, you see those f's of mu upper h's. Those are polynomials in Q with non-negative coefficients. And in fact, you can take this Poincare polynomial and write it as a sum over the partitions mu of n of a polynomial k tilde lambda mu of Q multiplied by the f mu upper h's of Q. So here's an example of what I mean. These are my Schur coefficients for my symmetric function expansion. Does anyone know what these things are? If I plug in Q equals 1, I get a Koska number. In general, these are the sort of modified Koska-Fox polynomials. They come up when you study Hall-Littlewood polynomials. So these are sort of very well-known things in symmetric function land, representation theory, and somehow this product combination is exactly the thing. So one thing I could do is I could try and recover this data by studying affine pavings of these nilpotent Hessenberg. Okay. Yeah. Yes. I want to do co-charge, not charge. Okay. The mysterious co-charge statistic. All right. So this is giving you a little context for why you might want to obsess about these things and spend years of your life thinking about them. Okay, so let's go back to thinking about Hessenberg varieties, because the other theorems I want to say really focus on, well, what can we say about some of these varieties? So let me write down one big theorem. It's one of the only theorems I know how to state for all Hessenberg varieties all at once without specifying either the Hessenberg function or the matrix. Here's one unifying thing that's true about Hessenberg varieties. So what my work in Hessenberg varieties is in part motivated by a talk I saw by Tomasco on this theorem back when I was a graduate student here. So it's truly all full circle. Sadly, it wasn't in this room, otherwise that would be a little too much. But the theorem is that all of these Hessenberg varieties, pick whatever matrix you want, pick whatever Hessenberg function you want, these are all paid by F. This is a type A statement. If you want some other types, then you can look at my PhD thesis. So that was like the motivation for thinking about this theorem. But I'm talking about type A, so this is Juliana's result. And so pay by affines means that I have a stratification of this variety into affine pieces. It's just like the Schubert cell stratification of the flag variety. But then what do? You intersect your Schubert cells with this variety, and you kind of hope that they're nice. In general, they might be very ugly, but it turns out you can pick X in its conjugacy class appropriately. So you can keep a handle on that. And those intersections are still affine. And affine pavings means that I'm allowed to put the Q to the 1/2 here. It means all odd cohomology vanishes. So this Q to the 1/2 otherwise might be a little mysterious, but because I have an affine paving, I only have even Betty numbers. So, all right, I am interested in geometric properties of Hessenberg varieties again, because they might encode some combinatorics. So I'm going to ask a very basic question. What is the dimension of a Hessenberg variety? Because after all, the title of this talk is Dimension Stability for Hessenberg varieties. Okay. And this theorem actually tells me a way to get an answer to my question, because what can I do? So here's the first answer. So the first answer is, well, Tomasco has an affine paving. I look at the affine paving, I look at all the affine cells, I compute their dimensions, I find the maximum dimension that occurs, and that's the dimension of my variety. So the answer is that I'm going to compute the maximum dimension of a cell in the paving. So now it comes down to studying these pavings. And the question is like, well, how tricky are these pavings? Like, how difficult is it to understand these cells? And I guess one thing I want to say is it's not that it's difficult, it's just that the cells in the affine paving really depend on X. Let's fix H for a second. Let me fix my H. And now I'm thinking about different conjugacy classes. Well, the things that index the cells change as we vary over conjugacy classes, and they can look kind of wild and different, and Colleen has code that tells me all what they are. And so this is sort of a non-trivial problem. Like, I don't know exactly which cells are maximum dimension. So let me show you an example, or just how to think about this in one example. So let's suppose X really is exactly this one we were interested in up here, nilpotent of Jordan type lambda. And so if you want the affine cells are in bijection. Of this nilpotent Hessenberg variety. So this is in Tomasco's affine paving, are in bijection. With particular tableau. I thought we haven't seen enough tableau, so we need some more tableau. So they're in bijection with what I'll call H strict tableau of shape lambda. So what should I mean by H strict? I have my tableau of shape lambda, I put 1 through n in there. What does it mean to be H strict? H strict is going to mean that when I see I and j next to each other in a row, I only care about the rows in this definition, then to be H strict will mean that j, let me make sure, yeah, j is less or equal to h of I. So, okay. H strict tableau, okay. The screen makes it much easier for these examples. So I can show you some non-trivial examples. One result, okay. So here's a Hessenberg function. This is the Hessenberg function, hi goes to I plus 1, to make it easy for me to quickly see what's going on. And I can already see that I have a problem. Make sure I write down the statement correctly.
I was thinking H.
That's what I thought. Okay, thanks, Paul. I'm always confusing my I's and J's. Let's go to H to J, because I can see it in this example. Okay, so here's a not H strict tableau. Okay, so I have a 7 and a 3. H of 3 is 4, but 7 is not less than or equal to 4. So this violates my condition. So actually what you should think of is that every single one of these tableaux, even if you're not H strict, corresponds to some Schubert cell. And then if I'm not H strict, the intersection with the Schubert cell and the Hessenberg variety is empty. Okay. So then the ones that are strict, there's some Schubert cell for each one of these H strict tableaux. And the Schubert cell for this tableau, if I'm H strict, actually intersects the nilpotent Hessenberg variety. And this is telling me there's an affine cell for this tableau. So I have this very concrete list of combinatorial objects. And now I can study and I can ask, okay, like out of all the cells indexed by H strict tableau, which is the maximum dimensional cell? Yeah.
So what is H of 7?
1, 2, 3, 4, 5, 6. Just typo. Here we go. 7, 7. This
is 7, 6, 8. Actually, there you go.
So yeah, okay, great question. This is okay. Why is this okay? So if I were just wanting increasing rows, this would be bad. But H of 6, this is my typo, should be 7. I'm sorry about that. Yeah. Because at some point I thought the tableau would be more interesting if there were extra box. And so had n equals 7 instead of n equals 6. Cool. Okay. And okay, so this is great. This is just for these nilpotent things though. So then you're like, well, now I want to think about more general kind of conjugacy classes. There's still an affine paving. But now the indexing things for the affine paving are multi-tableau, not just tableau. And there are also dimension formulas. So now you're like, okay, well now I need to compute the dimension. There is a way to read off the dimension of these cells from the tableau. It's very technical. I'm happy to go over the definition with you later. I read off certain inversions, but then as I vary over different conjugacy classes, there's different rules for different inversions depending on how they fit in the multi-tableau. This is a very technical kind of thing that happens. All right. So, okay, the basic motivating question, which is what's the dimension? Compute the max dimension of a cell in the paving is not such a satisfying answer because I cannot tell you what it is. Let me just cover another example and then state the theorem. Well, I told you that in special cases, we can usually say more about these varieties, right? The paving theorem is like one of the only theorems I can say with all conjugacy classes, all Hessenberg functions. But here's a very special case to consider. Well, let's let X be a regular matrix. If it's regular semi-simple, diagonal with distinct eigenvalues. If it's regular nilpotent, one Jordan block. Regular in general means the dimension of its centralizer is as small as possible, which is exactly dimension n for GLN here. Then there's actually a lot more that you can say. So maybe I buried the lead a little bit. Then the dimension of the Hessenberg variety is the sum over from I equals 1 to n, hi minus I. Which, if you go back to sort of my peak path way of thinking about Hessenberg varieties, some people call the area of the path, right? It's the number of boxes between the path and the diagonal. Okay. And this works for any regular matrix. And there's actually a good reason for this. It's because if you think about this map, right here, when you restrict to regular matrices, you get a flat family. And if you have a flat family, all the fibers of the family have to have the same dimension. Okay, wonderful. Well, okay, one of the reasons that happens here is because the Hessenberg varieties have what are called, like, this is like the expected dimension. If you were going to sit down and write down algebraic conditions defining these as subvarieties of the flag variety, you'd have exactly this many. So these regular Hessenberg varieties are the ones that have your expected dimension. In general, the dimension can be bigger. You no longer get the like flat family immediately. So let me say two theorems which sort of help this direction. So one theorem that maybe. So regular elements are very nice. Before I sort of say the theorem, let me go back to thinking about my algebra, my Lie algebra of GLN. Okay. So instead of actually thinking about conjugacy classes separately, I want to group them all together. I'm going to put all the regular conjugacy classes together. And there's a way to do this in the literature with what are called sheets. So there's a decomposition of my n by n matrices into disjoint sets. And each of these G lambdas is a union of conjugacy classes that all have the same dimension. So this is called a sheet. So one thing that I realized when we were studying these regular matrices and the flat family is that the regular matrices are a special case of a sheet, just if your lambda is n. And then in general, for G of lambda, you can think about, okay, like orbits of a fixed dimension. So one orbit that's always in the sheet is a nilpotent orbit of Jordan type lambda. Say this thing. So, okay, I have some examples of sheets here, but I'm a little out of time. So if you have a general matrix, you can look at a sort of generalized Jordan blocks. Those determine some partitions. You add up all the parts of those partitions and it tells you what sheet you belong to. So this is a very combinatorial sort of systematic way of keeping track of orbits using their generalized Jordan blocks. Okay, so everything contains a unique nilpotent orbit. And well, what are the semi-simple matrices? It turns out that a semi-simple matrix is in a sheet if it's conjugate to a diagonal matrix with distinct eigenvalues, where it's the transpose partition that determines how many times each of these distinct eigenvalues occurs. So the theorem is that we don't know if we have a flat family anymore, but we do have one of the consequences of having a flat family in these more general sort of setting where we group things together based on what sheet they belong to. So the dimension of all Hessenberg varieties defined over the same sheet G lambda is in fact constant. We still don't have a closed formula for it. But the trick is that we take all these sort of complicated multi-tableaux and we're able to sort of figure out a subset of the affine cells where the maximum occurs. And show that for things over the same sheet, this maximum is exactly the same. So this is the theorem with myself and Colleen and the Gumi. Here. Which is almost ready for publication. It's like 20.
You still assume regularity.
What?
You still assume regularity.
No, I don't need, so now, you mean the matrix? The matrix doesn't have to be regular anymore.
Does not.
No. So so each one of these sheets has one nilpotent orbit in it, for example. So it says if you're going to study this question of all, like what's the dimension over all these Hessenberg varieties, you might as well study it for the nilpotent ones. because every matrix in a sheet is in the same sheet as a nilpotent one. So then that's good enough. So this is actually kind of surprising because I no longer have the sort of expected dimension. I don't have any kind of automatic flatness for the family. I just know now, using this sort of tableau argument, that these all have the same dimension. I don't know, I'm surprised by it. So anyway, okay, thank you for your attention. I'm out of time.
Questions for Martha?
I saw one for sure.
If it's like the fixed each, like.
Yeah, for each fixed h. Okay, right, because the dimension really depends on the Hessenberg function. So we're gonna fix the Hessenberg function. Thank you. And we're taking x over the sheets. So this is a theorem about like the data of the Hessenberg function, aka the like path, the path that you're picking to define this variety is fixed. And when you fix that, you focus on this. Now, that being said, there are like different h's where the dimension over this thing could still be the same. So that's another interesting question. So I think it's a very interesting and open question to classify, like it always works if x is regular, but to classify the x's and the h's where the expected dimension is actually realized. Because this does happen for some examples where x is not regular.
Question.
Other hands.
So the H6 tableau, they're getting you like certain different, they must come from permutations, right?
Yes, yeah.
So is it easy to see where the permutations?
Oh, yeah, it's not so hard. And the only issue is that I will probably be off by an inverse. So I think that the permutation is given by just reading these numbers up the columns from left to right. It's sort of a convention from Tomasco's paving paper, or maybe the inverse of that. The inverse, okay, Colleen is probably the inverse of that. So that's the Schubert cell, like very concretely, that would be intersecting this Hessenberg variety. Yeah. Oh. All right. Sure.
Okay, two questions. One is, how much do you need to know about the conjugacy class? Is it just the sizes of Jordan's locks and which eigenvalues are equal, or even some of that is not necessary? I'm not saying about this theorem in general, when you talk about Hessenberg varieties, like maybe you don't need to know the exact conjugacy class. So that's my first question, and my second question was about stability in the title of your talk.
And so I guess maybe stability was just saying, the stability is referring to the fact that like this measure of how big the Hessenberg variety is constant over these sheets. Maybe I've used a mathematical word accidentally.
And then go to zero or something.
No.
Infinity, sorry.
Stability in sort of an English word sense. This number is stable. Maybe this number is constant. Dimension of Hessenberg varieties are like surprising constant dimensions.
Robust.
Yeah, something like this. And then when you say like, what do you really need to know about the conjugacy class? It depends on the precise information you're interested in, because it is true that different conjugacy class matrices will give you different varieties. So like in terms of just like the Hessenberg variety, Hesse, okay, right? Like you have this thing. Right? If you take x's from different conjugacy classes, you get different varieties, not isomorphic varieties.
Only? That's my question.
I think almost always. Maybe there's some like still like okay, I could take a constant multiple of the identity for x.
So it depends on the
No.
modular, like what eigenvalue exactly you take? That would be surprising.
So it is true that it does sometimes depend on the eigenvalues themselves. So there is a paper from last year or the year before where they study X regular semi-simple, and they do prove that the choice of eigenvalues will change this variety up to isomorphism.
Oh,
They're homeomorphic, like their cohomologies are all the same.
right.
But like the actual choice of eigenvalues do give you distinct varieties. Like a lot of the times, if you're interested in how many components they have or what are the Betty numbers, those things are not gonna depend on the eigenvalues themselves. So in some sense, knowing the distinct eigenvalues, how many distinct things there are is enough. But okay, if there's some more careful, like up to isomorphism, then no, that's not quite it.
Sam?
And the assertion of your theorem false if for other types.
Probably not. But it needs a bit more of a precise formulation.
Sheets are general.
Sheets are general. The problem is that I don't. Okay, first of all, the problem is I haven't fully thought about it. And then the second problem is I think there's a version of the statement in all types. The other problem is that I don't always have an affine paving. There's some non-trivial conditions on the X then that I need to take. I think probably as long as you have nilpotent part, regular, and a levy, the argument will go through, but now I have to do a slightly different combinatorial argument. I don't have my tableau anymore.
I think we've won that question.
Yeah, so for kind of compute dimensions, all you need to do is pick one matrix sheet, right?
That's exactly right. So you can pick your favorite matrix in the sheet. So you could take the nilpotent matrix and then just worry about H-strict tableau and then take a max over the dimensions for the H-strict tableau. You could also take a diagonal matrix in this sheet. And there, the affine pavings are slightly different, but it's actually a little easier sometimes to compute those dimensions. And you can use that kind of formula to find the dimension.
I was gonna ask, like, how easy is it if you were allowed to pick your favorite? Like, is this, you didn't say.
I don't have this nice closed formula. I would suspect that's what's gonna happen is there's gonna be a bunch of cases where this is the dimension, right? And like I said, I think it's an interesting open problem to classify. If X is not regular, when is this true? And then when you have that classification, then you'll be able to think about like, well, what are the like conditions when this is not true? And how would you write down this closed formula? That's still like an explorable question. I know that myself and Colleen and Megumi thought a little bit about this in like a very special case where the sheet is like lambda's a hook. So there you can be a bit more precise about some of this. I'll have to think back on what we kind of said, but yeah, I think there's open questions if you were like, I want to find when this is true. And then if you understand that, then you can start trying to figure out exactly how this fails. And that might lead to a closed formula.
So it might be good to
Okay. Talk more. There's a nice break after this.
We'll break till 3:45, but before that, let us thank Harada and Robichaux.